All right, I think we're ready. Well, today we're continuing with beams, but in a little bit different way. When we first started, well, the first thing we did with beams was we did frames and machines and said that at least one of the pieces in a frame or machine was a beam. And then we did frames and machines for a while. Then we started looking at beams flexing so that we could figure out their flexural stress. We drew shear and bending diagrams. And now we're ready to put all that together with the addition of maybe we're dealing with a beam that is not a standard shape. And so we have to figure out what is that beam's moment of inertia. And so that's what our focus is today, but we'll do it in the context of a bigger beam problem that we'll solve. So let's go down over here. This little chart that we're looking at is kind of representative of the types of charts that you'll see when it comes to moments of inertia. We actually did a moment of inertia-ish problem last time. We were, oh shoot, there we go. We don't need the touchscreen working. Let's see, it was not there. It was maybe there. There it is. So we had solved this beam. Actually, this was a piece of a frame, and then we figured out the forces that were acting on the frame. We only considered the y direction forces because the x was doing a different thing. It wasn't flexing the beam. Then we drew the shear and bending diagram, and then we said we want to find the maximum flexural stress, and we said that the beam was this little rectangle. So it's not a standard beam. It's not one we go look up in a chart somewhere. And I gave us the equation right here in the yellow box about how you calculate the moment of inertia for a non-standard beam. And I just told you to believe me that that was the value. So that's where we left off at. So now what we're doing is here is a chart of several, 1, 2, 3, 4, 5, 6 different shapes of kind of your primitive shapes, triangles, circles, parts of circles, and I saw an ellipse down there and a rectangle. And you can see all of these on the far right column. There are all of these equations. And the very first one is actually the equation that we were talking about last time. I got my cursor on top of it, but right there we've got the it's kind of small, but that is the BH cubed over 12. We'll write them larger when we're actually using the equations. So on Canvas, there's one of these charts. You can just type in moments of inertia for 2D cross sections or planar sections or something like that and find similar charts. But they're pretty standard, and these equations are universal for these shapes. So you don't have to worry about like the wrong chart. Now there are some of these that are for volumes, and we're not doing that. We're doing areas. In fact, if you remember a long time ago, we were doing centroids, and we had the idea that the centroid, we had made up a bunch of assumptions so that we were talking about the centroid of an area versus the centroid of a volume of some mass or whatever. And we said that maybe y sub c, the centroid in the y direction, was equal to, one of the things we said was integral of y dA over the total area. And we called this numerator here, we called this the first moment of area. Well, a moment of inertia, you see all these I values here. There's some J's in there too, that's a different thing. But the I is the moment of inertia. And if we were to write a similar equation, it would look like this. So the integral of y squared dA. And we would call that term the second moment of area. And it would be second because it's y squared, where the first one was y times dA, y to the first power. So we're not going to need to integrate these things, the integral of y squared dA. We're going to use the predetermined values from these shapes over here. just like we did last time. So let's set up the problem we're going to solve. I've already picked one out. I picked out this guy. This is one of the optional problems, number 12 on the optional set 2. And it looked like a good one to do. It doesn't need us to draw the shear and bending diagram on this one. So it's one of the ones where you can kind of see this section AA. We've just determined by some process that that's where we're interested in solving for flexural stress. So I'm going to copy this one, and we will try and solve this guy. And then we'll have to do some more complicated ones than this, but we'll start with this. All right. So the ultimate thing is this. It may be small on your screen, but over here it's asking us for sigma top and sigma bottom. So that's the flexural stress on the top of the beam and the flexural stress on the bottom of the beam. Looking at this beam, it definitely looks like there is tension on the bottom of the beam and compression on the top based on its loading. And and they show us the cross section looks like a T. And we do have some standard T-beam shapes, but this is not one of those. This one is kind of, I guess we made it ourselves, custom made T-beam. And we want to solve sigma equals negative m times y over I. We want to solve that equation. So m, we can get that relatively straightforward. We'll do that in a second. Y, we'll need the centroid to find y. And actually, we'll need the centroid to find I also. So in our little chart up here, there is no T-shape. We're going to have to construct this T-shape from two rectangles, basically. So relatively easy process for us to do to start out with, but that's where we're going to start. All right, let's do the stuff we already know. And let's find the maximum bending moment, M, on section AA. So to do that, I am going to draw a rectangle. Let's see, I don't know what tool I have selected here. Something like that, we'll say. And don't need that. Let's just show that it's a T-beam by drawing a line across there. Kind of looks like it's the edge of the flange on the top of the T. We also had a distributed load somewhere. Let's see, it looks like it goes to maybe there. And it has a value of W, which is 3.5 kilonewtons per meter. And then we have a pin at A, so that'll generate a Y direction reaction, AY. It'll also generate a X, although that's going to be 0 for X. We can just go ahead and zero that guy out because there's no other forces in the X direction that we can see. And then we have a roller over here, so that's a BY. And we have a couple of dimensions. These are actually given on the diagram. We have 2 meters over to the end of the distributed load. And we have another 2 meters to where B is located. Okay. We're going to find... Oh, well, let's go ahead and draw. Section AA is, somewhere over here. And we can, make a couple of dashed lines there. All right, so section AA is somewhere, I guess, 3 meters to the right of the support. So the support at A. So if we put that down here, this distance, 3 meters. Okay, Let's go ahead and lump our distributed load. We can do that when all we're trying to do is, find reactions and stuff like that. It's when we're drawing the shear and bending diagram that we don't want to use that lumped version. That's why one of the reasons I always draw it in a different color. Oh, wow, that's gigantic, though. Let's make it a little thinner than that. And its value is going to be 7 kilonewtons. 3.5 kilonewtons per meter. That's distributed over 2 meters. So 3.7 times 2 is 7. Or 3.5 times 2 is 7. And the location of that will be 1 meter in. Like that. All right. Now, in order to solve the concentrated moment, it looks like it's going to be easier to deal with the right-hand section. Maybe, this part of the beam, because there's nothing there except for By. So that means I need to find the value of By. So to find By, I'll do summation of moments about A. Okay, so let's see, AX, we've already decided 0. AY does not create a moment about point A. We have 7 kilonewtons, though. 7 kilonewtons with a 1 meter moment arm minus By with a 4 meter moment arm. So, therefore, By equals 7 divided by 4. 1.75 kilonewtons. And if we wanted to solve for A, we could do that, but I'm not going to use it, so I'm not going to solve for it. What I'm going to do now is I'm going to cut the beam on section AA, and I'm going to draw the pink side. And I'm going to draw the pink side because it looks easier to draw. There's less stuff going on. And remember, well, let's go ahead and put our By on there. Well, I want it to do that. Except I keep clicking the wrong button. There we go. And remember, I need a certain orientation for internal shear and bending. I don't often draw this side of the diagram, but the shear is going to be here. Not too interested in the shear force here. This is what I want to know. I want to know the moment, and I guess we can call it the moment on section AA. And then I've got this one dimension, which would be 1 meter, right? So if I solve my moment equation, I would get the shear force. Oh, I guess I do need to know the shear force, don't I? Because it's going to create a, oh no, I'm doing the moment about the cut. So the cut is, that little surface. So I don't need that one. I'll just have MAA, the moment at section AA. I'll give it a plus sign because I said clockwise moments were positive. And then minus 1.75 kilonewtons with a 1 meter moment arm. So therefore, the moment on section AA equals that equals 0. Move things to the other side of the equal sign and it becomes positive 1.75 kilonewton meters. All right, so we have that part. And now what we need is to fill in the other pieces. So we've got M. So we need Y and I. So this Y value, now you got to keep all these Y's correct in your head, straight in your head, because when we're doing the moment of inertia, we're going to introduce new values for Y. So keep track of which Y is defining what value. This one in the sigma equals my over I equation, it is the distance from the neutral axis of our cross section to whatever point we're interested in. Remember, this problem is asking us to solve the stress on the top one time and the stress on the bottom of the beam on another time. And so that y will change if I'm going to the top of the beam or the bottom of the beam. I don't know if we've run into that before, because we've been doing like a rectangle and an I-beam where the neutral axis to the top and the distance from the neutral axis to the bottom are the same value, just one's negative and one's positive. But here, with a T-shaped beam, there is an actual difference in the magnitude. But in order to do that, we need to know the centroid. So now we've got to get this little cross section and figure out where the centroid is. So let's go down here and let's try to draw a larger version of our cross section. So it's something, let's see, do I need it to go further than, we'll go there. And we'll go somewhere down here. I don't know if these dimensions are the exact ones. Oh, no. AA is not the neutral axis. They gave us those here. So AA I'm using because that's what they named in the problem statement. They named the cut line AA. That's a common, not necessarily AA, but using the same letter is a common way to show cross sections on a part layout, maybe a shop drawing or something like that, where you're going to make this part. That's a pretty common notation, to have a dotted line and then the same letter on either side of the line. Normally you start with A and work your way up the alphabet. And so that's a pretty common way of denoting that, hey, I want to do a cross section on that line. So it's not the neutral axis. Speaking of the neutral axis, that's what we need right here. What we're trying to do here is we want to know the value for y, this y in our equation, and it's measured from the neutral axis. So I've drawn out our little T-shaped cross section. I haven't put our dimensions because I don't know what they are. They're given here. So L1, 115 millimeters for the stem and the flange. All right. Okay, I didn't draw arrowheads on everything. I'll go back and do that. All right, so what we want to know, and this part is for finding the y that goes in the flexural stress equation, and for being able to calculate the moment of inertia for this T shape. So we want to know where the neutral axis is. So it's going to be, I don't know, somewhere here. We just don't know exactly where. So what we have to do is we have to go in and find the centroid of our T-shaped cross section, and the neutral axis is going to go through that centroid. So we did centroids several weeks ago. So that's it's been a while since we've done that. But this one is relatively straightforward. There's one rectangle here and another rectangle here. So the one is the flange and 2 is the stem. And we're going to use our little, what do you call it? We're going to use our bookkeeping method. It looks like we're getting a little iffy on the stream. I don't know. We'll see how that holds up. Here I'm just drawing something that reminds me of what part is what. So in this case, I only have 2 parts, but it's not crazy that you would have way more than 2 parts. So right now we just have 2. We're going to calculate the area. These are in millimeters, so this will be millimeters squared. So part 1 is 115 times 30. And part 2, part 2 is also 115 times 30. So our total area is just 6,900 square millimeters. Okay. Now we will, what I like to do is I like to go in and kind of indicate where the centroid of each part 1 and part 2. So we'll put there, and we'll put there. Now I need to measure the distance that they both are from some reference axis. Normally, we're going to use the x-axis, or the bottom of the beam, as our reference. So here, the height I just drew is 115 divided by 2, 57.5. That's for part 2, though, so let's put that in the y value over here for part 2. And then part 1 is, where can I put that one? We'll put it, I don't like crossing other dimensions, but that's what we're going to do. This one is 115 plus 15, so it's actually 130. So that's an important part if you haven't done a centroid in a while, remembering that we have to measure everything from the same axis, and I'm measuring from the bottom, the very bottom of the stem. Now we can do AY, A times Y. 3450 times 130 is a big number, 448,500. And 3450 times 57.5, slightly smaller number, 198,375 over the total area. So that is 646,875 millimeters cubed over 6,900 millimeters squared. So the units are going to give us just millimeters. 93.75. So what that is this distance. We'll kind of do that. And I mean, that's roughly, I didn't scale anything correctly necessarily, but that looks like what I would expect. For a T-beam, the neutral axis, the centroid, where the neutral axis is located, is closer to the top. So that seems reasonable to me. All right, so now we have a way to find the y value in our equation. We have 2 different y values because they're asking us for 2 different things over here. So y for the top, let's go ahead and write those numbers down. So therefore, y for the top value equals, let's see, the total height of the beam is 115 plus 30, but then we're going to subtract off 93.75 is equal to whoops, put the wrong number in, 115 plus 30 minus 93.75 is 51.25. So from the neutral axis to the very top surface of the beam is 51.25 millimeters. And we'll use that number when we're calculating the stress on top of the beam. And similar, the bottom is, well, it's just the neutral axis, y sub c. But since I measured from the bottom of the beam, then 93.75 Now, technically, that's a negative number because I'm treating the neutral axis as 0. And so I have to go downward to the bottom of the beam, so a negative direction. So y sub c is negative, or well, y to the bottom, not y centroid, but y distance from the neutral axis to the bottom of the beam. It's negative 93.75 millimeters. Let's see, there was something I was going to mention. Oh, we didn't calculate x sub c, right? We didn't do, where's the x centroid located? There's two reasons for that. One reason is this is a symmetric beam, and so if we just put the y-axis down through the center of the beam, like if we just did y right here, and x is that way, then the x sub c would be 0. So since there's symmetry, it's bilaterally symmetric, so x sub c would be 0. The other reason we didn't calculate a x sub c is that we loaded this beam with the load forces, this distributed load being perpendicular to the neutral axis that I've drawn here, which is in the x direction. And so I don't need to even worry with any loads coming in from the side. This beam doesn't have any, so I don't need to know anything about loads that might be perpendicular to a vertical neutral axis. It does have a vertical neutral axis, but since there are no forces perpendicular to that, I can ignore it. We need I. All right, so how we're going to do I goes back to this guy. So here, that is the equation for the moment of inertia of a rectangle, but you see two of them. There's also this one. So you have to look careful. I wonder if I can zoom in enough to where you can see this. It's going to get blurry, but we'll go back to our regular size in a minute. So the distinction here, first of all, they're different equations. BH cubed over 12 and BH cubed over 3. So they're different things. But the real distinction is that little prime symbol right there. I just wrote on top of it in red. So I'll make it, right there. The top equation, the one in the top box, has that prime. The one in the bottom box doesn't have that prime. And if we look at our picture, I've got x prime here, but I've just got plain old x here. So these are two different axes. I'm going to say that until you've done this a while and you know what you're dealing with, you need to use the prime numbers, the prime equations. There's a technique that we're about to use called the parallel axis theorem, and it can only be applied to the equations that are going through. Maybe they won't always be labeled prime. The reason that it's different, though, is notice where it goes. It goes through the centroid of that shape, of that rectangle. So that's the key to it. Whatever axis that goes through the centroid of your shape in your chart, that's the one you want to use for now. Because we can use the parallel axis theorem on that axis, we cannot use the parallel axis theorem on some other axis. Basically, like this x-axis at the bottom of the shape, it has already had the parallel axis theorem applied to it, so you can't do it again. So until you know enough about what all that means, we'll just leave the x there. Until you know enough about what that means, just use the equations that go through the centroid of your shapes in your chart. So in this chart, those are the x primes. Let's see, I don't know how far out I'm zoomed, but that looks sort of like where we started. All right, so we can use our existing diagram that we drew for the T shape, so we can work on that one. And what we're going to do with it is we're going to apply that equation. So let's go ahead and get that. In fact, maybe I can copy that, just that part. just that guy. And we'll copy it down here just so we have it handy. Okay. So, and we're only going to use the top one. We're not going to use this bottom one. We're not going to use that. There, not using that one. All right. So let me rewrite the equation in case it's too small to see on your screen. So what it says is I x prime equals b h cubed over 12. That's what the equation that we are going to use is telling us. And on the diagram, you can see maybe it's also too small, but this is b and this is h. So they kind of look the same when they're small because b and h are similar shaped letters. But the base is b and the height is h. So what this will give us, this equation will calculate the moment of inertia of a rectangle, because that's what we're looking at here, about its own centroid. Okay, and so they've got the centroid C labeled. It's in the very center of a rectangle. So that's great, except that if I'm looking at my T shape here, I've got those two centroids labeled, and they're not at the neutral axis of the whole shape. So this equation by itself is not going to be enough. First of all, I'll need it twice because I've got the flange part 1 and the stem part 2. But then those equations that I would calculate bh cubed over 12 for those shapes, those would give me the moment of inertia or moments of inertia about the wrong spot. I need the moment of inertia about the neutral axis of the T shape because that's the cross section of the whole beam. So that's where the parallel axis theorem comes in. So this is the parallel axis theorem. We'll say I nu, so the new axis, equals I original plus a times y squared. This is the parallel axis theorem. That's not parallel. How do you spell parallel? Like that? Parallel axis theorem, where in this case, well, where in all cases, A, the area of the part, in this case, the part is either part 1, the flange, or part 2, the stem, but it could be whatever part. Any of the parts could be, you know, any of these shapes. And here's another y value. So this is a different y. And let's see, y is the distance, how do I want to put this? Between the axes is what I'll put. So the parallel axes in this case are, I have two sets. I want, this is the T shape that I'm dealing with. I want to calculate the moment of inertia for this T about its own neutral axis. I have equations here that will give me the moment of inertia of a rectangle about its own axis, about its own centroid. So the distance is I need to take this axis for part 1, and I need to move it down to the neutral axis of the whole shape. That value is y. For the stem, I need to move the axis that goes through the centroid of the stem. I need to move it up to the neutral axis, and so it has that distance. So there's the distance is the y in the parallel axis equation is the distance between the axis that goes through the centroid, you know, this guy, the centroid of the individual part, the distance between that axis and the neutral axis of the entire cross section. So here's how that's going to look. So I'll have the moment of inertia for part 1 equals the original moment of inertia for part 1, which is bh cubed over 12. I'll write it out in variable form, and then I'll put the numbers in. Plus the parallel axis theorem part, the area of part 1, times the distance y between part 1 and the neutral axis. And that y needs to be squared. So these numbers are b is 115 for part 1. I want to leave the units off because it'll get really cluttery with all the little m's in there for millimeters. The height of part 1, 30 over 12, plus the area of part 1, 115 times 30, times the distance between, times that guy. The distance between the centroid of part 1 and the neutral axis of the whole thing, which is 130 minus the 93.75. Let's see what that is. 130 minus 93.75. 36.25 is this distance. So that's the value for y. And that is squared. Okay? So if I plug that in, I will get numbers. Oh wait, this bh cubed, that 30 in the first part there, that h is cubed. So 30 cubed times 115 divided by 12 is 258,750 millimeters to the fourth, plus 115 times 30 times 36.25 squared. Only the y is squared, not the ay. So plus 453,3515.625. So 4.5 million compared to 260,000. So these are big numbers. Again, these are millimeters to the fourth, though. But notice just the shape, the flat flange shape has a large number, 260,000 millimeters to the fourth, and large values of I. They're in the denominator, so large values of I are going to reduce the stress, right? Because they're in the denominator of the equation. So I get way more stiffness, by having the parallel axis theorem part. And the parallel axis theorem part is accounting for the fact that this flange is raised up above the neutral axis. So what that's telling me is that if I can get material away from the neutral axis, it will increase the stiffness of that beam. That's why you have T-beams and I-beams where those flanges are moved out away from the neutral axis in the middle of the beam. Let's do the stem, so part 2, and do the same thing and look at what its numbers are. So I2, same thing, BH cubed over 12. It's a rectangle, so it has the same form, plus A2, distance between 2 and the neutral axis, squared. So here, the base for this piece is 30, and H is 115, and that's the number that's going to get cubed. So I'm going to get a really large number there. Plus the area, which is the same area. And the distance, let's go back to our picture. The distance here is that distance. So what is that? 93.75 minus 57.5 is 36.25. Don't really have a lot of room to write that, but there it is. Oh, that's weird. That does not always happen that way, where y is the same value. I think it's just because our pieces are the same piece, 115 by 30. But that's just the way it worked out. Either that or we made some error somewhere. So don't count on these two numbers always being the same number. That's not true. All right. So let's add all this stuff up. 115 cubed times 30 divided by 12. So I get a giant number here. 380,2187.5 millimeters to the fourth. So 3.8 million. And then I'm going to add a little bit. Oh, that 36 was squared. 36.25 squared times 115 times 30. 453. Oh, that's the same. Yeah, it's the same number. So the stem here is contributing way more than the flange. The flange by itself is not doing a whole lot. It's a large number, 260,000. But then when I raise the flange away from the neutral axis, then it starts to contribute more to the stiffness, reducing the flexural stress. But the stem is doing a lot by itself. And you can actually easily visualize that if you just think about a ruler. You know, think about a ruler and how you would bend it. You know, it's laying flat and you'd bend it pretty easily. But then you turn it on its edge and try to do the same thing, and it would be very hard to bend, almost impossible to bend the ruler on its edge. You know, trying to bend it. Do I have a ruler around here anywhere? There's one over there. So really easy to bend that way, you know, not much effort at all, but to bend it that way, pretty impossible to bend it, you know, if I'm trying to make it bend up or down when it's like this orientation. And what I've done is I've got a rectangle like the stem here, and here I've got a rectangle like the flange as the cross section. So very different experiences trying to bend that ruler in two different directions. That's the same, that you can see it with the ruler. Here you can see it with the numbers. We need to add all this stuff together though. So the total moment of inertia is all of this stuff added together. I, for the neutral axis of our T-shape, is I1 plus I2. So let's see what that is. 258,750 plus 4,533,515.625. I'm going to say times 2 because there's 2 of those numbers. Plus 3,802,187.5. So if I did all of that adding correctly, I have 13, 12, 7, 9, 6, 8.75 millimeters to the fourth. So if I want these units to work out, this equation here, my over I want it to give me something like pascals or megapascals or something, then I need to be careful with my units and make sure they're all working the way I want them to do. So I'm going to just convert everything to meters and newtons, I guess. The moment's already in Newton meters or kilonewton meters. So I'm going to do everything in newtons and meters so that the answer I get will come out in pascals, newtons per meter squared. So here's a tricky spot that some people will make a mistake if you're trying to do this conversion. So 13 million millimeters to the fourth. Oh, millimeters, there's 1,000 millimeters in a meter. So you just divide by 1,000. But that's not how you convert millimeters to the fourth power. So if you want to convert, yes, there are 1,000 millimeters in 1 meter, but you've got to raise that conversion factor to the power that the millimeters are in. So raise it to the fourth power. So essentially, you've got to divide by 1,000 4 times. So if I want to put this in meters to the fourth. So I'm going to do that. I'm going to divide by 1,000 4 times. And then I get a really small number. 1.31 times 10 to the negative fifth meters to the fourth. So a different direction on, a really tiny looking number where I had a giant number before. All right. Let's see if we've done this correct or not. So sigma equals negative m times y over I. Let's do the top of the beam at section AA. So sigma on section AA and the top equals negative m. That was so long ago I don't remember. 1.75 kilonewton meters, which is 1,750 newton meters. Times y to the top of the beam. That was y to the top is 51.25 millimeters. So 05125 meters. Over 1.31. I'm sure there's lots of rounding going on there. Times 10 to the negative fifth meters to the fourth. So that will give me units of newtons per meter squared, which is 1 pascal. And let's see how many pascals we have. 1750. Oh, yeah, I did the top of the beam. Yeah, okay. So plus, oh no, not plus, times 0.05125 divided by, how am I going to put this in here? 0.1234131. 6.846,374.05 pascals, which would be, let's see, 6.85 megapascals. Let's go ahead and do the bottom of the beam and see how we're doing. Oh, negative because of the negative sign in the equation. So negative indicating that it's a compressive stress. Sigma for section AA at the bottom of the beam is same moment, 1750, or negative from the equation, 1750 newton meters from the bending moment on section AA. Y for from the neutral axis to the bottom of the beam is this negative 93. 9375. And the moment of inertia is no different. It's the same because it's the same cross section. All right, 1750 times 0.09375 divided by 0.1234131. Those were 4 zeros. This number comes out positive because I have a negative times a negative. So positive 1252385 pascals. So that would be 12.5 megapascals. It is a larger number solely because the Y value is different. Let's see if these are the right numbers at all. I don't know. I didn't check beforehand. Let's see. Oh, I've already logged out. 6.8 and 12.5. That's what we had, right? 6.8 and 12.5. I might have gotten that other one 6.85 and they had 6.83. Maybe it would have given it to me. I don't know. Actually, I had 6.846. So hopefully that would be close enough for web work. There's a lot of rounding in that denominator for sure. All right. So that is from start to finish how we would take a beam equation, or not a beam equation, a beam problem where they're giving us a specific location. If we had this same setup, but the question was find the maximum flexural stress, the thing we would do different is instead of doing this process, we would have gone in and we would have drawn the shear and bending diagram and found the location of the maximum. Where did the bending moment peak? And so that would be different about this problem. On an exam, I have to break this into lots of little pieces because it took us an hour, basically an hour, to do this one thing. Now there's a bunch of stuff we did in there. We had to find the centroid, we had to find the bending moment, we had to find the moment of inertia for the cross section, which required the parallel axis theorem. We had to apply all that to our equation. So there's a lot going on in here. This would be many problems on an exam, or at least a problem with lots of individual answers if it was an exam problem. All right. Let's do some that are just moment of inertia, not the beam part, because I think we've done enough beams for a while, but we haven't done all of the things you might encounter with moment of inertia. So let me see if I can find a good problem where it's just calculating moment of inertia. That one might be kind of fun. We don't know the answer to it, but let's look at how this one would work. Not solving the beam, just the moment of inertia. So here, this is 2 flat plates, the darker gray, and 2 channel beams, standard channel beams, all welded together into some super I-beam looking thing with a hollow center. Let's see if we can find the moment of inertia of this thing. We're going to need what D and W are, though. Let's see. We need this. Don't need to be that large. Okay. So 240 by 30 millimeter steel plate. So what that's telling us is that's 30 and that's 240. And then they've told us C254 by 45. That tells us it's a standard beam, and we can go look up some stuff about it. Oh, let me answer this question first. Is the Y above always positive? Yes. the y above, because what if there's more than one force being applied to different directions? Oh, so yes, there could be a lot of forces applied, like distributed loads and point loads. They could be pointing all different directions. There's only one bending moment at a section, though. So it's the bending moment, this what I called MAA, the moment on section AA. That's what's causing the flexural stress. The forces, all the external forces, are creating the internal bending moment. So it doesn't matter all the external forces, well, they matter, but their direction doesn't dictate the plus or minus necessarily. They create the internal bending moment, and it tells us if the beam is bending with tension on bottom of the beam or tension on top of the beam. Clockwise moments create tension on the bottom of the beam, and counterclockwise internal moments, I should have said internal that first time, internal moments, counterclockwise internal moments create tension on the top of the beam. So it's and there's only one internal bending moment on every little section. It can change from one end of the beam to one end of the beam to the other end of the beam, but for every section, like we have here, section AA, there's only one bending moment inside that section. So, and yes, the neutral axis is the reference point, and anything above the neutral axis is a positive y. Anything below the neutral axis is a negative y. But the bending moment on that cross section, the internal bending moment, it could be plus or minus depending on if it's clockwise or counterclockwise. So I don't think we've done any problems where there was a internal bending moment that was counterclockwise, because that's not as normal. That means that there's tension on the bottom of the beam, which means the beam is bending upwards somehow, which is unusual. It's it's not normal. It's not as common. It could happen, but it's just not as common. All right, back to finding C254 by 45. I'm going to have to go to our reference material and hope that I have the C sections right there. And we need, all right, so we're going to have to get another sheet. So you cannot take, like, this is the US sheet, right? US customary units. You cannot take and convert these over to metric units, because there's too much rounding in there. You maybe in a bind you could do that, but it won't work for an exam or anything like that. So let's go to exam reference and find the C table in there. I don't know which one it's in. I don't see it in 1, so let's look in 2. There's a C. That's the C, but it's the one that we just looked at. All right, it's there. It's upside down, so we need to rotate that guy. Did we get it? All right, there it is. Let's zoom in on that. That's as much as I can. So it's in here. Let's copy this and see if we can make some sense out of it. I've lost the cursor. There we go. Okay. Now it's a little crooked, but let's see. We wanted 254 by 45. So 254 by 45 is right there. See if we can. I don't know if I can. Well, the problem is I don't want it to be a straight line, I guess. So let's see if we can. There we go. All right. We need to decide if we're dealing with the XX or YY set of columns. So you look here, and XX is the horizontal one. In fact, that shape looks exactly like this shape orientation, right? So it looks like we will deal with the XX. Now, I don't know. Let's look at our original problem statement. Yeah, so you can kind of tell that the forces are being placed on top of the beam. So the forces are coming in from this direction. So I want the axis, XX or YY, that's perpendicular to those forces. If you can't really tell, or it's not like explicitly said one way or the other, then it's going to be the XX. All right. So I don't want these YY numbers over here. Don't want that. I want to use the XX stuff. So I is this column. And I want this number right here. And the units on that are weird. 10 to the 6 millimeters to the fourth. So I've got 42.9 times 10 to the 6 millimeters to the fourth. That is the moment of inertia for any of those pieces about their own centroid. So fortunately, this cross-section that we've fabricated here, the centroid is right in the center. You know? That distance is just 254 plus 30 divided by 2, so the total height divided by 2, 157. And the centroid for the C shapes land right on top of it. The centroid for the darker gray shapes are not on top of it, so I will have to use the parallel axis theorem for the plates, but not for the channels, the C. And I don't have to go find the centroid. I can do it by observation, just that the part is symmetric about this neutral axis that I've drawn. All right. So let's see if we can get the neutral axis, not the neutral axis, the centroid for our combined super I-beam shape. So I'm going to say that this is part 1, this is part 2, 3, and 4, just so we can keep track if we're labeling equations. All right. Part 1. So I1, the moment of inertia for part 1, equals the moment of inertia for part 1 as it's originally given, plus A1 times y between 1 and the neutral axis squared. So the original equation, this is a rectangle. So we just did a rectangle. BH cubed over 12. If you don't remember that, you can go back to our chart here and reference that. Plus the area of part 1, which is B times H again, times the distance is 157 minus 15. So I'll give you a second to make sure you can do that. So 157 is the distance from the neutral axis to the very top of the beam, and then from the centroid to the top of the beam, the centroid of the part 1, that distance is 15 millimeters. So 157 minus 15 is 142. And 142 is the distance here. And that's the distance that goes in this parallel axis theorem. Let's put the other values in there since I wrote just B and H. So the base for the top plate is 240. The height is 30 cubed, BH cubed, over 12, plus 240 times 30 times 142 squared. I'll put the squared inside there just to be super clear. So that number is 30 cubed times 240 divided by 12. It's 540,000 plus 142 squared times 30 times 240. The total, if I've done that correct, 145720800 millimeters. Those are all millimeters to the fourth. Now, if I were to do the bottom plate, I would have exactly the same numbers. Technically, the 142 would be minus, right? I have to go downwards to get there, but I square it. So negative 142 squared is the same as 142 squared. So this is also the same number I would calculate for what I call I2. So I2 and I1 are the same number. Same value. The neutral axis height, the 157, I got by taking the entire height of the beam and divided by 2. And so hopefully the entire height of the beam is 254 plus 30 is 314. And 314 divided by 2 is the 157. And I know it's in the center like that because all these shapes are symmetric. Like the neutral axis is an axis of symmetry, horizontal axis of symmetry. If for instance that bottom plate wasn't welded on, I only had the plate on the top, then it gets a lot more complicated because I have to find the centroid of that shape. Kind of looks like a pi symbol or whatever, and that would be harder to do because for the channel beams I only have the information in the chart here to help me, and so it'd be a little complicated to do. Okay, I guess we could do it, but no need to. Part 3. So we've done 1 and 2. They're the same. Part 3 is its original value. It is not, oh, actually, part 3 is just its original value, because the centroid for part 3 is already landing right on the neutral axis. So all I have to do is say that it is 42.9 times 10 to the 6 millimeters to the fourth, and that's just straight out of the chart for the C254 by 45 channel beam. And 4 is the same thing. So the total moment of inertia for this guy is equal to I1 plus I2 plus I3 plus I4. And that is, I don't know, let's see. 145,720,800 times 2. There's 2 of those. That's the plates. Plus 2 times 42. And then 9, 1, 2, 1, 2, 3. I think that's it. Equals, I think, 3,772, 416, and 2 zeros. That would all be millimeters to the fourth. And then if we wanted to convert that to meters to the fourth, we could do our little conversion factor like that guy that we did last time. 1 meter over 1,000 millimeters, but it's millimeters to the fourth, so we have to raise our 1/1000th to the fourth power. And so now we could take that, and if we wanted to calculate flexural stress or something like that, we could use this as our moment of inertia. Let's see, what time? We have a little bit of time. Let me see if there's another type that would be, that's not even a moment of inertia. That's, I don't want to do that one. I want to find a specific type. We've already done a T-beam. Maybe that one. Let's do this. Oh, let's see. Okay, we can do this one, or at least part of this one. So we're not going to do the part through the centroid. So that would require us to find the centroid of this weird shape, which we could do. We know how to do that. I just don't want to do that part again. We're going to do something a little bit different. Let me make sure I don't have a better problem. Oh, yeah, okay. We'll do this one. And we'll find this part A down here. Or at least A for IX. So we'll find the first blank. That's our goal. And that should give us a good sampling of all the different things that we might end up doing. Okay. All right, let's make that a little bit larger. Let's label our stuff because it's all written in the text. So L1 is 55 millimeters. So those are both 55. L2 is 170. R is 30. And, oh, that L1, there's another L1. 55. Now, this one, be careful what it's asking. So notice where my axes are. So here's an X axis. Here's the Y. Well, I didn't even get close. There's the Y axis. The first part of this problem is actually asking for the second moments of this area. So that's the moment of inertia with respect to the X axis, which is this bottom. That's not the centroid of the shape. So you don't have to calculate the moment of inertia about the centroid of the shape. You only have to do that when you are trying to do the flexural stress equation, but technically you can find the moment of inertia about whatever axis you want. And so you might end up, at least for exams and homework like this one, we might just give you an axis. So mainly so that you don't have to go find the centroid and then do the calculations. So we might just give you an axis. Here we're just saying use that x-axis that's given and find the moment of inertia for this wedge shape about that axis. So this works a little bit like centroids where I'm going to have two positive shapes. You know, there's actually nothing in there. So I'm going to have a triangle, a half circle, and then I'm going to have one negative shape, a circle in the middle that's cut out. So each one is going to create its own moment of inertia about the x-axis. And then we're going to give the circle, the cutout circle, a negative moment of inertia to account for the fact that it's not there. It's missing. So part 1 is going to be our triangle. Part 2 is our half circle. And part 3 is our punched out hole in the middle. All right. So I1 is equal to, let's go to our chart and let's see if we have a triangle. And we, in this case, we're going to violate one of the very first things I said today about only using the x prime. Now that we've done a little bit with it, hopefully we can know that we don't have to use the x prime equations all the time. So there's the triangle, and sure enough, they have a triangle sitting on an x-axis, and they have an equation for a triangle about its base or bottom surface. Well, I guess it's not a surface, line. It just so happens that that equation is also BH cubed over 12. So that could be a little confusing, but that's just what it is. So this moment of inertia B is 170. H is the height of the triangle, which is 55 plus 55, so 110 cubed over 12. And this one does not need the parallel axis theorem because the moment of inertia that this equation is related to is the bottom line of the triangle. And that bottom line of the triangle, this line, it's already on my reference, the x-axis. It's already sitting on there, so I don't need to move it anywhere. So let's see what this number is. 110 cubed times 170 divided by 12. 1885583.3. These were all millimeters, so millimeters to the fourth. Let's see if we get that lucky with the half circle. So let's go find our chart. There is a half circle. Actually, they don't even give us a moment of inertia for a circle that way. We're going to have to look at a different chart. So we do have a half circle here, but they only give us the moment of inertia of this circle about that bottom, the diameter. And we need one in the other direction. So we need another chart. Let's go to our exam reference and see if we can find... there's moments of plane areas. Let's see. There we go. We need this one. Oh, wait. Let's go back to our problem statement. All right. So what we've got here is I do have this. So I've got that equation. That says IY. Now, that y-axis is right here. But the moment of inertia about that axis, which if you take and if we were to redraw this circle in the same orientation of our circle, let's see if I can even get close to that. So that's the way our circle is shaped, right? So if I translate what they have, they've got the centroid somewhere right here, and they've got that thing coming out, but they labeled it Y, right? So we sometimes have to mentally rotate or redraw it the way that we need things. They said that IY equals pi r to the fourth over 8. The only problem with that is that on our original diagram, that's this axis. So we are going to need to use the parallel axis theorem with this distance. And that distance is just given to us, it's 55. So they just told us that distance. It's also the radius of the circle, if you can tell, or the radius of the arc. So let's do that. So pi r to the fourth over 8 plus a of part 2 times y for part 2 squared. So those numbers would be pi 55 to the fourth over 8 plus the area, which is the area of half of a circle. So pi, it has a diameter of 110, pi d squared over 4, but it's 1/2 of that. So pi 110 squared over 8, actually. Times y squared, which is 55 millimeters. All right, so there's a lot going on in that one. You may have to spend some time making sure that you know where all of those numbers are coming from. They equal, let's see, 55 to the fourth times pi divided by 8 plus all this other stuff. Plus 55 squared times 110 squared times pi divided by 8. Uh-oh, we didn't like that. Let me try that again. 55 to the 4th times pi. Why is it not liking that? Oh, whoops. I'm doing the wrong thing. All right, times pi. There we go. Divided by 8. Plus 55 squared times 110 squared times pi divided by 8. All right, so I think it's 17967210.17 millimeters to the 4th. Okay. Now we need I3. I3 is a hole, so it's going to have a negative, and it's a circle. So let's go see what a circle is. Doesn't really matter what axis because it's a circle. It does matter where the axis is located, but it says that X and Y through the centroid, they label it the origin in this case, but through the centroid are pi r to the 4th over 4. Negative pi r to the 4th over 4. But that's about that same axis that we just had, so that's not going to work. Plus area of part 3 times y of part 3 squared. Got to remember that this whole term is going to be negative though. So pi, it has a radius of 55. Again, there's a negative sign in front of everything. An area of pi d squared over 4 times the y distance from the centroid origin of the circle down to my x-axis, because in this problem is specifically asking about the x-axis, is 55. So I've got lots of 55s in there. So let's see if we can do that math. 55 to the 4th times pi divided by 4 plus 55 squared times 55 squared times pi divided by 4 equals 143,73768.14 millimeters to the 4th, but that's a negative number. How'd I get... Oh, wait, no, that's an old question. Let's see. So now, let's add and subtract these and see if we're anywhere near what WebWork wants. 18855.833.3 plus 179,67210.17 minus 143,73768.14. If all of that's right, the moment of inertia about the x-axis, so the bottom of this diagram, equals 22449275.33 millimeters to the 4th. Now, just plugging this into my calculator and not really checking things, there's a high chance of failure here, but let's... Oh, and it wants it times 10 to the 6 millimeters to the 4th. So actually, let's see, 22.45 times 10 to the 6 millimeters to the 4th. So let's try 22.45. That'll maybe help with some of our rounding issues. Let's see. Oh, we were off 27.6. That's what I was afraid of. There's a really good chance that somewhere in here, since I wasn't checking anything, I was just plugging in the first number that I got. There's a really good chance I either wrote something down wrong or calculated one wrong. I'll run through them quickly and see if I am just missing something. The first one looks okay. Let's see about these others. Oh, shoot. Times pi. Second one looks okay. See about the last one. Maybe make sure I use pi r to the 4th over 8 for that is what I wanted to use. And then the circle, pi r to the 4th over 4. Let's make sure I didn't write any of my units. I mean my, oh, I did. Oops, sorry. I used 55 in here for the area, and it's actually, I have it on my diagram, it's 30. So that's my problem, or at least one of my problems. Let's see if that fixes us up. I was just being careless, I'm afraid. All right. Around the same number of places for this. Yeah, so as far as the round out the same amount of decimals in general, yes, 2 and 3 decimals are fine on an exam. Is this mechanical engineering physics? Sort of. It falls under statics. So it falls under the category of statics. This class is statics and strength of materials. This little topic, you could probably argue that it's engineering physics, but we would call it statics. Oh, no, not high school. Well, I guess technically the math is, but the concepts aren't. Let's put my right numbers in here. 30 to the 4th times pi divided by 4 plus, let's see, pi times 30 squared divided by 4 times 55 squared. Hopefully my order of operations are going to work out here. I wasn't paying a good enough attention there. 2774419.012. That's all negative. I'm afraid. Oh. I'm afraid I. Did I put the wrong. Hold on. That should be y is 30. Yeah, 55 squared times 30 squared times. I keep putting add instead of multiply on this thing, and it is not working. Well, let's see. I'm not seeing where pi d squared over 4. I'm not seeing where we're getting a different number, because it wanted 27, and we're getting, like, if you add these, we're getting like 34. Where is our little problem? this might be a job for MathCAD or something versus little calculator to get this to work out right. It's kind of why I didn't want to work this problem, but I want to figure out where we went wrong. Let's see, BH cubed over 12 for that should be fine. The half circle, pi r to the 4th over 8 should be fine. But we have to add the area, which we did. We did pi d squared over 4, but divided by 2 because it's a half of a circle. And we took care of the 55, unless I wrote L1 is 55, L2 is 170. No, I wrote all those right. Yes, so what degree is this for? It's all of them. So let's see. How many elements are... I'll answer the lab question in a second. I really want to see where do we not have a number plugged in right? Or am I just not plugging it in the calculator right? Oh, geez. It's right here. That's a 15. All right, so I don't know if I'll plug them in again or not, but that was... We'll get 27 point whatever, 27.6 times 10 to the 6. So what I had done is I had put in a diameter when the equation clearly says put in a radius. So that was a problem. So I fixed it. I just didn't recalculate it. So on your question about Lab 1. So Lab 1 has to do with SolidWorks. And what's going on there is, since we can't actually go to lab, since we're virtual, we're going to simulate a lot of the same type of things. And so you are simulating a tensile test. And you're doing that with a process called finite element analysis. And what that does is, instead of like we haven't really done, I guess, kind of like here. So that's a stress equation, right? But it applies to like the whole cross section, here. Another way to think about that is that, well, this one cross section has a whole bunch of different stress in it. In fact, we calculated stress on the top of the beam and on the bottom of the beam and got different numbers. So another way to look at it is to, instead of thinking of this as one T-shaped cross section, you can think of it as a bunch of like bricks, little bricks that are arranged together to make that T-shaped section. So like a bunch of Legos all snapped together in the shape of a T. And then you can look at every one of the Lego bricks individually and calculate its stress based on its neighbor stress and your boundary conditions and all that. All that's the math that's happening inside SolidWorks. So the mesh word that your question's about, the mesh is how many bricks are there in there. And you can control that in SolidWorks. The way I showed you to do it is kind of just take all the default settings. But if I think over on the the left-hand side of the like tree that you walk through, the history, there's one that's called mesh. If you right-click on that, I think you can either do properties or display mesh or mesh properties or something like that, and it'll just tell you how many elements there are. There'll be thousands, you know. Even at the default setting, there'll be 1,000 elements or something, or more than that even. Is 30 not the radius? No, 30 is not the radius. 30 is the... Oh, wait. No, that's the problem then. So I did it backwards. This is the problem. Good catch there. 30 is the radius, but over here I've used diameter, so that should be 60. Yes. Is that the only place that we did that? Yeah, I think that's the only place we did that. So yeah, 30 is the radius, but that makes the other part of the equation wrong where I did the area, because I was doing pi d squared, pi diameter squared over 4. And I put in the radius. Is the due date for Lab 1 correct, July 30th? Yeah, I think that's probably a good time. There's plenty of time. Some people had asked about using the virtual machines because maybe they were using a Chromebook or an iPad or something that wasn't going to run SolidWorks. And I have not seen... I tried to log into it, and I couldn't this morning. So you might check the help desk at school and see if there's some reason that you can't log into the virtual machines. Maybe you have to be on campus, or maybe you have to run a VPN. I'll try that. I just didn't get to load up the VPN before the stream started here. Now I want to calculate this thing and see if we can get the right answer. You can go ahead and go if you're not interested in seeing if this is the right answer or not, but 30 to the 4th times pi divided by 4, so that's a different number, plus 60 squared times pi divided by 4 times 55 squared. So now I get 9189158.5 negative. Yes, those numbers give me 276338884.97 millimeters to the 4th. Oh yeah, good. You had already calculated it. Yeah, so my problems were all right here. And they had to do with just going too fast. Those are hard to track down on an exam. You will have at least one problem on the exam where you have to calculate the moment of inertia about some axis, maybe the centroidal axis, or maybe just the x-axis like this one. And it really is a tedious little thing, and there's not a trick to it other than being careful with your numbers. I was not being careful with my numbers. Let's see. I think we're probably at a good stopping point. I opened up homework 15, so you'll see that one. And quiz 3 is open. Exam 1 should be totally corrected. So if you go in there, you should have your final grade. If there's still something that doesn't look right, then you can send me a email about a particular question. But I've gone through everything, and unless I missed something, I've checked off all the stuff that Canvas couldn't check, and corrected some things that it didn't do right. So those should be done. Quiz 3 should be open now, and Lab 1 should be doable. All right, SolidWorks doesn't allow me to move free. I know. Yes, that's okay. So you don't have to tumble. You know, that's called tumbling. In the you can do everything from the front view. Even for your simulation, you can do everything from the front view, and you don't even have to do anything because at least Lab 1 is a flat part of sample. So you just draw the shape, the cross section, and then extrude it into the screen, and you don't even have to rotate. So it won't be a problem, at least for Lab 1, and I don't think it'll be. Lab 2 might be a little bit more tricky, but you don't have to tumble around. I'm not sure why it's doing that, like why it won't let you do that, but it could be that maybe you're not, you don't have a third mouse button, maybe the wheel, because I think that's the tumble button. Does the help desk have a phone number? Let me check a little quickly here and see. I know they do most stuff by email. There it is, 5300, or an email. Most of the stuff they do is email, but they do have a phone number. If anybody's there to answer it, I'm not 100% sure though. Yes, and so on the SolidWorks stuff, Miss Ashley in the new building, she handles most of those installations also, and she might know something about the virtual machines or know who to ask. And if none of that, I know that at one time you could actually check out a laptop from maybe the library, maybe. There was some place you could check out laptops to do particular activities. Maybe that would be a third option. All right, we'll be back, but it'll be next week, Monday, and I think we're getting close to the end of beams. Let's see. What are we? Oh, we have actually no. We have a whole week left of beam topics, and then we can finally take an exam on it. So we are going to do design of beams. That's actually a really easy topic, and then beam deflection. 2 lectures on that. It's interesting. It's another one of the It's another one of the tedious things though. So it's another. We'll do some simple problems, but we'll do some more complex ones. For the complex ones, we'll have to break out MathCAD or something like that. All right. I will see you all Monday.